Hello. In the previous video on central forces, we had already deduced the Kepler's law, and it was the first law that we had deduced, where we had obtained the general equation of a conic section, which was of the form L divided by R is equal to 1 plus E cosine of theta minus theta primed. And the E there is the eccentricity, which is equal to the square root of 1 plus 2 E, which is the total energy, J, which is the angular momentum squared, and then divided by the mass times of m into times of k squared, k being the constant of the force considered. Also, we had the value of L to be equal to J squared divided by mk is the value of L. We also express the eccentricity as E is equal to J squared A divided by mk, where A is that area that is covered by the planet during its motion for a given interval of time. In this case, A was in the solution part of the deduction that we had made, and we had obtained the expression for the values of eccentricity. For different values of eccentricity, we were obtaining different values of energy, and thereby different forms of conic related to those eccentricities. Now we will be obtaining the Kepler's second law, and as far as the second law is concerned, we have the second law to be of the form dA by dt to be equal to half r squared theta dot. Now remember, this is what we had obtained or moved over to while deducing the expression for the central force in the first video of this series. To be exactly at 35 minutes into the video, I had mentioned you to take a note of that expression, because that is going to be effective, and that is what we are coming up to, because this value is constant, and that is what the second law is all about. The second law states that the aerial velocity of the planet, that is the area swept by the planet per unit time, is always a constant, and it is proportional to the angular momentum J, as you can see in this equation. Now this constancy of aerial velocity is actually the general property that takes place under the central force, and the gravitational force is a special case of the central force, and that is the reason why we are getting this right away. Now we move over to the third law, which states that which is the relation of the between the semi-major axis and the time period of the planetary motion about the sun. Now suppose we have the sun somewhere in here, which lies at one of the foci, and then we have a horizontal line through it, and this point, which is dividing the horizontal line into two parts, from there on we are considering another vertical line, again with the point bisecting that vertical line. This gives the path of the planet about the sun, which is lying over there. more or less an elliptical path I have managed to draw. And this is the sun at that point that we see over here, that is the sun. And let the planet be at a radial distance r. The planet is at the point P, and then the closer distance, the closer path of the planet to the sun is what we term as the perihelion, and the other one, the far off distance from the sun during its motion, the farthest that is denoted over here by R2, and that is known as the aphelion. So R2 is the aphelion and R1 is the perihelion. Now this distance, the half of that total distance of the perihelion and the aphelion, is the semi-major axis, while the other half is the semi-minor axis. Now during the course of motion, this angle that is subtended by this radial distance of the planet with respect to this perihelion is what we are considering as the theta minus theta dash. That is the angle that is expressed in this conic equation. Now if that angle theta minus theta prime, let me use another ink for you. If this angle theta minus theta prime is equal to 0, then we have a cosine of theta minus theta prime to be equal to 1. As a result of that, we get the value of r to be equal to simply r1, which is the minimum most value of the radial distance. Then again, if we have now this is one condition, let's assume another condition, that is theta minus theta prime to be equal to pi. Now if theta minus theta prime is equal to pi, cos of that is going to be minus 1. And if that is minus 1, then we are getting r to be equal to r2, which is the maximum possible value, as I said, the aphelion. Now with these things available to us, we can rewrite this expression as follows. That is L divided by, instead of r we have for the perihelion we have r equal to r1 when cos theta is plus 1, and so we are left with 1 plus e on the right hand side, and that implies r1 should be equal to L divided by 1 plus e. Then for the aphelion we have the value theta minus theta prime to be equal to pi, and so we are left with 1 minus e on the right hand side. That implies r2 is equal to L divided by 1 minus e. Now from this what we can get is that A is equal to r1 plus r2 divided by 2, that is the total length and the half of it, and that is equal to, we can take the L as common in both those right hand side equations that we see, and we are left with 1 by 1 plus e plus 1 by 1 minus e in brackets, and they will equate to L divided by 1 minus e squared. The 2 that comes up in the numerator gets cancelled with the 2 in the denominator term. So this leads us to the value of A, which is equal to, we put the value of L that we had previously discussed, that is J squared divided by mk, and then we use the value of 1 minus E squared, which we had obtained in the previous video. If you can check that, that is mk squared divided by 2 E j squared, and this will be negative and the negative can come over here, and that will imply A to be equal to, well, you can see that the j square terms get cancelled out, the m term get cancelled out, one of the k's is cancelled out, so we are left with A to be equal to minus of k divided by 2E, or we can say that the total energy is equal to minus of k divided by 2A. As you can see over here that the total energy term that we have obtained is now k is a constant, of course. The total energy term is completely dependent on the inverse of the semi-major axis. Then moving over to the second part of derivation, where we need to obtain the relation with the time period of motion of the planet about the Sun. We know from the second law that dA by dt is equal to half of r squared theta dot, and that implies dA should be equal to this term over here multiplied with dt. Now if the time period is t, that is the complete time taken by the planet to move in its orbit about the Sun, one complete orbit, then we have the total area to be equal to the integration from the over the dA part, and that is going to give us the integration over this term. And now because you know that this term is equal to j by 2m, so we can bring in the j by 2m over here just to get out of that theta dot and the t time that is to come up over there. So to get out of that mess, we just use this constant term, and then we can integrate over dt from 0 to t to give us the complete time period t. And but as we know that the area of an ellipse with the semi-major and the minor axis, we have it to be equal to pi a b, so we can just compare j multiplied with t divided by 2m that we just obtained is equal to pi a b, so that gives me t to be equal to 2m pi a b. Now this is the relation of the time period with the semi-major axis, but also there is the semi-minor axis. How do we get rid of that? Well, we can just use the known expression of the ratios of semi-minor to the major, as b by a is equal to root over of 1 minus e squared, and then we have b to be equal to a of this, and then finally we get a, and because we know 1 by e squared. How do we know 1 by e squared? Well, we can put that value, because a is equal to L divided by 1 minus e squared, so we have j squared divided by mk 1 minus e squared, which is just substituting the value of L over there, and this is going to give us 1 minus e squared to be equal to j squared divided by mka, and that is what we are going to put over here. That is 1 minus e squared under root is simply root over of j squared divided by mka, and this is going to reduce it to root over of a j divided by root over of mk k. We'll use this expression for the time period, that is over here, that we had obtained for t, this one. So for t, we can get t is equal to 2 pi m a divided by j, that is over there. And as far as b is concerned, we substitute the value of b that we have obtained, that is root a times of j divided by root over of m k, or we get t to be equal to 2 pi a to the power 3 by 2 whole root of m divided by k. We can just square this term, and finally we obtain t square is equal to 4 pi squared a cube m divided by k. As you can see, we have done away with the b factor, so all we have is t square to be proportional to the cube of the semi-major axis, and this is the Kepler's third law that we had predicted prior to the derivation. We'll be continuing more with the topic on Kepler's law and the stability of the orbit, as mentioned towards the end of the previous video, but that will be in the upcoming videos. Till then, thank you for watching.